Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 4 of module 8. I hope you have been liking all the lecture happened so far. And in the earthquake seismology course, we are going to cover the concept that will be the topic for today is the composition of the D double prime layer. And before that, we will be having an overview of what we have learnt in the terms of the composition of the mantle. That was the topic of discussion in the previous lecture, but we will have some part of that into the lecture today. And then we will be having to know the composition of the core, and finally we will be having the summary of today's lecture. As far as the recap of previous lecture is concerned, we learned that the beta phase of the olivine, so because the olivine is the major component of the upper mantle and it is present in the form of alpha olivine, which is orthorhombic in nature, and it has H3P structure. So it turns out to the beta olivine, and that beta olivine transformation takes place at the 410 kilometer discontinuity. So after that, the beta transform to the gamma or the spinel structure, that is also known as ringwoodite, at a pressure of around 15 gigapascal, and that is corresponding to a less dramatic seismic discontinuity that is located at 520 kilometer depth, and then this gamma spinel breaks down to perovskite structure and magnesiosite at around 650 kilometer depth, and that basically the depth of the discontinuity in the transition zone. And perovskite is also known as brisbanite, and this is the major constituent of the upper mantle. Around 70% part of the upper mantle is made up of perovskite mineral. A simple univariant phase causes a sharp discontinuity in the velocity, while a complicated multivariant phase produces a velocity gradient. So basically, if we remember, then we saw a diagram here, then where we had a very sharp discontinuity where alpha was changing to beta. That was corresponding to a velocity structure where the velocity was sharply changing like this. And then we also saw there was the two phases, those were present together, and those were having the multivariant phase, and those were basically producing a velocity gradient where the velocity was gradually changing in this region. So if you compare both of these regions, here the velocity is sharply changing, here the velocity is gradually changing in case both of the phases are present or the coexisting. So after that, we learned that the olivine alpha to beta reaction should occur over a narrow depth range, and beta to gamma transformation should take place over a broader depth range, which agrees well with the lab predictions. And if you remember, we saw a graph where we had some transformation where alpha was changing to beta within a very narrow range, and then beta was changing to gamma within a very broad range. So it was a broad range. Here you had a very smaller range where the transformation was taking place. And then we learned that the gamma spinel to perovskite and magnesiosite transition should occur over a narrow depth range consistent with the observed sharpness of the 660 kilometer seismic discontinuity. For the D double prime layer, we suggested 4 models, out of which three models we studied in the previous lecture, but we will have an overview of what we have learned in regard to those all three models in the previous lecture. So don't worry, we will be covering those in the today's class as well. So for the D double prime layer, four possible models describe the observed characteristics. First is a simple convection model where the subducting slab is going down to the core mantle boundary, and then after it contacts with the core mantle boundary, then it gets risen up because of the high temperature, and that means the cold material that is sinking along the subducting slab to the core mantle boundary is getting heated up from the contact with the core and then rising up again. In the second model, that predicts that the subducted slabs do not reach the top of the core but remain separated by a chemically distinct layer that is known as tracks. So near to the subducting slab, it has like layered structure, and then near to the plume, then it has the vertical sheet-like structure. So in the horizontal layering structure, it basically represents the radial anisotropy, and then in the vertical sheet, that basically suitable for the azimuthal anisotropy. Another possibility is that the part of the subducted lithosphere that started as a basaltic ocean crust and then transformed to the eclogite transforms to a material that is seismically faster than the rest of the lower mantle. And let's start with the lecture today. And this particular flow diagram you have seen in the previous lecture as well, but we are keeping it here for the sake to have a revision of what we have learned, because composition of earth understanding is very important in order to understand how the earth behaves when the seismic waves travels inside the earth. So this is basically representing the composition of the mantle, and you have the olivine crystal that is located in the upper mantle in the form of fosterite, or it is known as alpha olivine or alpha phase, which is having the orthorhombic crystal system. And when you keep on increasing the pressure over it, and what will happen with depth at around 410 kilometer discontinuity, the hexagonal closed packing structure of the alpha olivine changes to closed center packing. Then because the pressure at 410 kilometer discontinuity is around 12 gigapascal, that is a huge pressure, and that alpha phase of the olivine in the form of fosterite changes to Wetzelite, that is the beta phase, that is also known as beta spinel cubic. And if the one thing must be remembered, we are not having any change in the chemical structure of these crystals, but the structure is only changing. The arrangement of the atoms is only changing, but the formula, chemical formula of alpha olivine and the beta olivine remains same. That means the chemical formula of fosterite and the westlite is almost same, is completely same, but their structure is different. One is having orthorhombic crystal system, and another one is having beta a spinal cubic system. So, or you can say beta spinel system. And as you increase the pressure further at around 520 kilometer discontinuity, that is basically a less dramatic seismic discontinuity, where the pressure increases to 15 gigapascal. If you remember, at 410 kilometer discontinuity, the pressure was 12 gigapascal, but now as the depth is increasing, pressure is increasing, and at around 520 kilometer discontinuity, that is the less dramatic seismic discontinuity, that is the pressure is over here is 15 gigapascal, and the Wesleite, that is the beta olivine, having the beta spinel cubic structure, changes to ringwoodite, that is gamma spinel. And then if you increase the pressure further as you go deeper down to a depth of around 660 kilometer discontinuity, the pressure here increases to 24 gigapascal, and at that point, at this discontinuity, the ringwoodite or the gamma spinel changes to perovskite, which is also known as bridgmanite. And here also there is no change in the mineralogy, only the structure change, and it is the most abundant mineral in the lower mantle, or you can say it is the most abundant mineral relatively in the earth as well, which is around 70% of the lower mantle. And if you go even deeper, and then when you reach to the core mantle boundary within the core at the base of the mantle where d double prime layer is located, this perovskite changes to post perovskite. And let's talk about the another mineral that is also present in the upper mantle, that is the pyroxene. And this pyroxene, as the pressure increases at around 1200 kilometer depth, it changes to garnet. And then garnet, as you keep on increasing the pressure at around 660 kilometer discontinuity, it changes to perovskite, and then perovskite changes to post perovskite. And in the detailed manner, if you want to look at the composition of the mantle, you can understand it by these two with these points. Like upper mantle comprises of olivine, and it goes into a series of phase changes at transition zone, and the alpha phase transform to beta spinel known as Westlight at a pressure of around 12 gigapascal at 410 kilometer discontinuity. So this 410 discontinuity is located over here, and across this discontinuity the alpha transform to beta spinel. That means the phosphorite changes to Westlight at around 12 gigapascal pressure, that is at this 410 kilometer discontinuity. Then at 520 kilometer discontinuity, where the pressure changes to 15 gigapascal, the beta phase transform to gamma or the spinel structure, and that gamma spinel is known as ringwoodite. And after that, if you even increase the pressure furthermore at around 24 gigapascal at a depth of 660 kilometer discontinuity, the gamma spinel breaks down to perovskite structure, which is also known as bridgmanite, as I told you. And there is another mineral that will also be formed after the transformation from gamma spinel to perovskite structure, and the magnesiowoodsite. And in terms of pyroxene, which is the another mineral that is present in the upper mantle, the pyroxene component that also undergoes changes, beginning with a transformation to garnet below about 200 kilometer, and this basically changes further at around 660 kilometer discontinuity to a magnesium bearing garnet, or that is known as majorite, that transformed to a structure called ilmenite. You can see there is the change. This is the ilmenite here. Beneath about 660 kilometer, the majorite or ilmenite transformed to perovskite, and some of the majority probably survives into the lower mantle as stishovite or a high pressure phase of quartz and an Al2O3 rich phase. The pyroxene and the garnet transformation that occurs basically gradually, and if you look at the transformation of alpha olivine to gamma olivine, that takes place basically very sharply. So pyroxene to garnet is very gradual change, but from alpha olivine to gamma olivine, the transformation is basically very sharp. So the pyroxene and the garnet transformation occur gradually and contribute to a high velocity gradient through the transition zone down to about 770 kilometer discontinuity. Now let's look at the composition of D double prime layer. We have seen a glimpses of it in the previous lecture as well. Now to start with, the seismic observation has produced a picture of D double prime region, and that basically tells that the lateral velocity variations are there at the D double prime region. Also there is vertical layering and anisotropy present. Hence the lithosphere at this particular D double prime region is basically going to be complex in comparison to the lithosphere. The D double prime layer, core mantle boundary, and the lithosphere, asthenosphere, these are thermal boundary layers. And this approximately may reflect factor including subducted lithosphere, the generation of mantle plumes, and interaction between the core and the mantle. The figure that you are seeing, so we are going to consider some models of the D double prime layer. Those are proposed. So this is the first model. We are going to study four models. So this, as per this model, this is the very simple convection model where the cold material is sinking down. Cold material is sinking down to core mantle boundary, and then it touches the core mantle boundary, which is basically very high, and because as soon as it touches, then it heated up, and then rising up again like this. So left side, this basically represents the resulting vertical velocity profile in the region of downwelling and the upwelling. Solid line is representing the region of downwelling, and the dashed line is representing the region of upwelling. And you can see that there is a reduction in the velocity of up to like 5% or plus minus 5%, and that is basically caused by the temperature variations here. And however, given the complex seismic structure observed, this model component seems necessary but insufficient. Now let's look at the model 2, that is another possibility where it is suggested that the subducting slab do not reach to the core mantle boundary, but it is separated by a chemically distinct layer. This is the chemically distinct layer that is basically separating the subducting slab from touching to the core mantle boundary. And it is said that this particular layer that is separating it is maybe formed from the early planetary differentiation and may have also grown by the chemical reaction between the mantle and the core. And high pressure experiments suggested that the perovskite and the magnesium that is present in the lower mantle would react with iron, and these mantle drags, because this layer is known as the drags, mantle drags, might be thinned in the region of the downwelling, and it is thicker in the region of the upwelling. And because this is basically accumulated over here in the form of layers, so it is responsible to produce the transverse isotropy, and in the region here it is basically accumulated in the form of vertical sheet, so it will be a region of upwelling and hence the azimuthal anisotropy. The velocity increase happens at the D double prime layer, so here the velocity is suddenly increasing at this discontinuity, and that may be partly caused by the ponded slab material, which will still be colder and have higher velocity than the ambient rock. And this discontinuity may be enhanced by drags that is basically flowing up and over ponded slabs. The third possibility, that is the model 3, is that the part of the subducted lithosphere that started as basaltic ocean, then transformed to eclogite transform to a material that is seismically faster than the rest of the lower mantle. This phase might have been delaminated from the slab and then accumulated, forming a different chemical boundary layer that is in the form of post crust. And if it remains solid, it might partially explain the D double prime discontinuity. And alternatively, if it is melted, then it will form the ultra low velocity zone. And either way, its laminar nature might explain the observed seismic anisotropy. And the lateral variation in the velocity would correlate with anisotropy, as such wave would travel fast in downwelling region because of the transverse isotropy. So here the transverse isotropy is present, because of which the SH wave would basically facilitate itself to travel faster but be slowed down in the region of azimuthal anisotropy. And the last possibility that we should talk about is that based on the D double prime may also signify the bottom of the perovskite stability field, and large radial changes in the temperature and or composition at the base of the mantle could move perovskite or a secondary phase out of its range of stability, causing a phase transformation. And one possibility is a transformation of the perovskite to stishovite and magnesiovite, which occurs with an increase in the iron and the magnesium ratio. Its tissue white has high seismic volume and might contribute to the D double prime discontinuity. In this case, anisotropy might reflect orientation of the crystals due to lateral flow. The denser magnesiowissite might settle to the bottom, forming the ultra low velocity zone. Given our limited knowledge, D double prime may involve these and other facts. Now, since we have talked about the composition of the mantle and crust, now the time to talk about the composition of the core. So that is the layer that is present at the very center of the earth, and it might have the composition similar to that of the iron, but with a less dense element of lower atomic number added. And if we look at the cosmochemistry, the meteorite that comes to the Earth can be roughly divided into the category of stony meteorite that may resemble the mantle, and there might be another form of meteorite that might be iron meteorite, and those are composed of iron nickel alloy, and which are thought to be similar to the core. And the convection of the molten iron that is in the outer core is considered to be responsible for the generation of the Earth's magnetic field. And the lighter element that basically lowering the core density, the possible candidates are sulfur, silicon, oxygen, potassium, hydrogen. And if you look at this graph that we have already seen in the previous class, which basically reflect towards the variation of the bulk sound speed with the density, and several minerals has been plotted their variations of the sound speed with density. So as the density is increasing, how the bulk seismic sound speed is taking place, the variation in it is taking place within the different kind of material that has been compared. And those, it has been found that the seismic bulk velocity is linearly related to the density in this region. And when we saw that, we found that the mantle density that is around 4.5 gram per centimeter cube comes out over here, and that is basically related to the material named as unite. And if we look at the core density, that is around in between 12 to or maybe 10 to 12 gram per centimeter cube, then it may comes into this region of the density, which is similar to the density of the core, which is on the left of the pure iron. So this is basically having a lighter element component coming into it, that is for the silicon. Now, if you look at these graphs, these are familiar to you. We have seen it into the one of our previous lectures. You can see that the various parameters such as the density, gravity, pressure, and the mass are varying with respect to the depth from surface to the center of the core. And this is for the density variation. Here is the gravity variation, where the gravity is smoothly increasing up to the core mantle boundary, where it becomes around 10.7 meter per second square, and then it is smoothly decreasing toward the center of the earth, and it becomes zero at the center of the earth. And this is the pressure, which is gradually increasing with depth, and this is the mass, which is gradually reducing with depth. And it may seem surprising that the inner core is solid, because it should be at the higher temperature than the liquid outer core. Since the temperature is very high as you go into the core, the inner core, as per our assumption, it should be the liquid, but it is solid. That is might be happening because of the pressure that might be increasing so fast, that is overcoming the increment in the temperature as well. Because of that, the density might be more in the inner core, and it is much more viscous than the outer core, because of which it is becoming solid. If you compare the temperature from the inner core to the center of the earth, the temperature is increasing only about 100 to 200 degrees centigrade. That is around 3% of the temperature which is present at the center of the core, that is around 500 degrees centigrade. But if you compare the pressure, that increases around 11%. That means from 3 to 9 gigapascal at the inner core boundary to the 364 gigapascal at the earth center, then the pressure increment is much higher than the increment in the temperature. So obviously pressure dominates over the temperature, because of which the inner core is solid. The density inferred from the seismological data is consistent with that for the solid iron expected from experiment and modeling. And this situation basically requires that the inner core geotherm be at the temperature below the melting point temperature curve, that is basically the solidus, whereas the outer core geotherm must be above the solidus, because outer core is liquid in nature, which is in the form of the melt. And for this purpose, there are two suggestions that are offered. One is case one, in which we are considering both inner core and the outer core are chemically identical. And there is another case where the inner core and the outer core are considered to be different and having different chemical composition. So if we consider the inner core and the outer core that are chemically identical, then the solidus, which is this solid line, should rise smoothly, and in that region of the outer core you will see the geotherm is above the solidus, which basically reflect that outer core is liquid, and if it reaches to the inner core it becomes lower than the solidus, so it becomes solid in the region of inner core. That might be the one possible suggestion, and this is what it is written here. The geotherm would be shallower. So if you consider the slope of geotherm and the solidus here, the solidus slope here is steeper, much steeper than the geotherm, which is shallower. The geotherm would be shallower than the solidus, so that they intersect at the inner core boundary. This is the inner core boundary here, and but steeper than the adiabatic gradient required for the convection in the outer core. In the second case, on the other hand, calculations suggest that the superadiabatic temperature gradient in the core required for convection should be steeper than the solidus. So you can see that the geotherm is much steeper, and here the solidus is shallower in this case, because both of the layers of outer core and the inner core are chemically different, so there is a offset in between them. Obviously, because the solidus for the inner core, since it is of having the other chemical composition than the outer core, they should be having different solidus curve. And if you look at their slopes, then the geotherm is much steeper than the inner core. And in the case of outer core, since it is liquid in nature, so the geotherm is above the solidus. In the case of inner core, the solidus is much above than the geotherm. If so, the solid inner and the liquid outer core can be explained by assuming that the inner core is chemically different from the outer core and thus have a different melting curve. Thus, only in the inner core does the geotherm lie below the solidus and result in a solid phase. And if we assume that there is a possibility of a light element in the core, because of that it is lighter in nature, so one of the promising candidate is sulfur, and this is the phase diagram for iron and the iron sulfide system extrapolated to the core condition. And since the sulfur is basically used to significantly lower the melting point temperature of the iron, so you can see that melting temperature of the iron is reducing, and the cooling a liquid iron mixture with 12% sulfur corresponding to 33% iron sulfide causes solid iron to freeze out, leaving the liquid richer in iron sulfide. So you can see this is the iron that is mixed with iron sulfide here, which is in the solid form which is in the liquid form in the outer core. So by this analogy, the outer core corresponds to the iron sulfide rich liquid and the inner core to the denser iron solid. The nickel would also preferentially enter the solid phase. Such a model predicts an inner core of approximately 80% iron and 20% nickel, and an outer core with 86% iron, 12% sulfur and 2% nickel. The inner core freezing is thought to be crucial to the convection in the outer core because the sinking iron releases gravitational potential energy. It has been estimated that the outer core's convection is driven in approximately equal fractions by this process, the latent heat of the crystallizing inner core and the loss of the primordial heat. And such models suggest that the boundary between the inner and the outer core is both a phase boundary and a compositional boundary like the core mantle boundary. It has also been suggested that iron crystallizes at the inner core boundary at some latitudes and dissolves back into the outer core at other latitudes constrained by magnetic forces. This effect may cause preferential alignment of iron crystal and thus inner core anisotropy. So this is the summary of what we have learnt in the lecture today as well as in the previous lectures. So what we have learnt is the ratio of the moment of inertia to the mass gives a scalar that depends upon density distribution. So if you remember, we talked about C upon ma square. That was the ratio of the moment of inertia to the mass, and we were trying to consider different models of the earth where we consider earth as a uniform material, and then we consider all the masses at the surface. Then we consider the earth as a two shell planet, and then we derived the Adam-Williamson equation, and this equation relates the velocity structure to the derivative of density with radius, and it goes like this: d rho as a function of radius with dr is equal to minus of rho r g mass with respect to radius divided by phi r square is equal to minus rho r gr by phi r. The drawback of Adam-Williamson equation is that it only considers the self compression, but it does not take into account the changes in the mineral phase with depth. So modified form of Adams-Williamson equation was proposed considering the effect of superadiabatic gradients, where it looks like d rho by dr is equal to minus rho g by phi plus g tau alpha, and alpha is the coefficient of thermal expansion and tau is the portion of the temperature gradient exceeding the adiabatic gradient. And F. Birch proposed that the inhomogeneity in the earth can be identified using this particular function, and we saw that after 900 kilometer the material is homogeneous, and before 900 kilometer depth the material behaves as inhomogeneous material. The pressure inside the earth can be computed as PR is equal to minus integral from 0 to radius r gr rho r dr. And then we learnt about the temperature variations, that is in the form of the geotherm, which basically reflects that the temperature variations with respect to the radius. The geotherm depend on the source of the heat modes by which the heat is transferred upward in the earth. An average thermal gradient is 13 degree centigrade per kilometer up to a depth of 100 kilometer, while a low gradient of only about 0.6 degree centigrade per kilometer up to the base of the mantle. So if you remember, we saw a curve where there we saw there was a temperature here, and here we had depth for in the mantle. So for the mantle we saw the curve for the geotherm was varying like this. Then it has shallower variations, shallower increment in the middle mantle, and then at the d double prime layer it rises steeply back up again. And this is the region where the thermal gradient was around 0.6 degree centigrade per kilometer, and in the region over here, that is the lithospheric mantle up to 100 kilometer, and at the region of d double prime layer where the gradient is steeper of around 13 degree centigrade per kilometer. And then we learned that higher temperatures reduce seismic velocity and strength but increase attenuation. Conversely, higher pressure increases the velocity and strength but reduces attenuation. So as you increase the temperature, attenuation will also increase, but if you increase the pressure, then attenuation will decrease. Temperature increase rapidly at d double prime layer, causing velocities slower than expected from the lower mantle velocity gradient. A high temperature in the core keep the outer core liquid, but the rapid increase in the pressure due to the weight of the outer core makes the inner core freeze into a denser solid. Then we learnt that a key result from experiment is that bulk sound speed and the density for a material are approximately linearly related for a given mean atomic weight. So this is the same curve we just saw. This is the curve they are talking about, where the bulk sound speed and the density are linearly related for various material in the for the earth. And then what we have learnt, that the dunite, that is a rock containing 92% olivine, which in turn is 90% phosphorite, fits the mantle data. Crust is predominantly basaltic or granitic depending upon the continent or the ocean. Upper mantle is mainly comprises of peridotite, and based on the pressure variation it may form such as olivine, clinopyroxene, orthopyroxene, garnet spinel or plagioclase. In the transition zone, the series of solid state phase changes occurs. In the transition zone, 2-3 discontinuities are there, where the olivine changes to its various polymorphs depending upon temperature. At 410 km discontinuity, olivine changes to westleite, and at 520 km discontinuity, westleite changes to ringwoodite. So westleite is a beta spinel structure and ringwoodite is a gamma spinel structure. At 660 km discontinuity, this gamma spinel structure ringwoodite turns to perovskite and magnesiowustite, and these are most abundant minerals in the lower mantle. Lower mantle's main constituent is perovskite, which is known as bridgmanite, and also there is magnesiowustite, ferropericlase. Outer core mainly composed of liquid iron alloy. It lies at 2891 to 5100 km, and at inner core, that is mainly composed of solid iron, which lies at 5100 to 6400 km. It has been also suggested that D double prime may also signify the bottom of perovskite stability field and transformation of perovskite to stishovite and magnesiowustite, which occurs with an increase in iron magnesium ratio. The density and bulk sound speed data suggest that the core has composition similar to that of the iron, but with a less dense element of lower atomic number added to it, that is silicon. The density inferred from the seismological data is consistent with that for solid iron expected from experiments and modeling. The solid inner core and the liquid outer core requires the inner core geotherm to be at temperature below the melting temperature curve, that is solid earth, whereas the outer core geotherm must be above the solid earth. And these are the references. So with that, we are finishing lecture 4 of module 8. Now we are going to meet in the next lecture. Thank you so much. Bye bye.